Okay, here's our next problem. It's not a typical optimization problem that involves like a real world scenario or a situation, a case study kind of thing that we've been doing with business or social sciences or sort of an engineering application. This is more just a good old-fashioned math problem, analytical geometry, I guess, if you'd like to classify it. We're trying to find a situation where the how close a point along a curve, in this case it's y equals the square root of x, okay, so that's a square root function. How close does any point along this curve come to a root, an x-axis here, 3 halves over comma 0. So the situation is to the right here on this particular diagram here. Here's our root function, right? And we've got this point, this arbitrary point P at xy, okay, just going along here, going along the curve. And we're trying to find the minimum distance between this arbitrary point P and the given point A, 3 halves, comma 0. So at somewhere along here, okay, if I can visualize this, we might have a minimum distance here. And this minimum distance, okay, is going to be found by making a triangle here and talking about, okay, this distance here. See, at any point, there's always a triangle made. Okay, so we're trying to minimize the hypotenuse of the triangle, right? I'm going to call this D, okay? Okay, so I'm going to call D be the distance or the length of the hypotenuse, okay, of a triangle. So our triangle, I can just pull it out of here. Our triangle has this point 3 over 2, 0, and this point x and y, I'm going to call it, but y is actually going to be the square root of x. I'm going to put my function in here. I'm going to make a right triangle. Okay, so I've got, so I need to figure out some lengths here. Okay, well, the length, okay, let's use this point. Let's use just a really rough basic, okay, basic distance formula here. So this point right in here, okay, it's going to be the x-coordinate of my given point P and the y-coordinate of my given point A. And that's the point x0, right? It's any point along the x-axis. Okay, so the distance formula, okay, or the distance between, okay, this distance in here is going to be, okay, delta x, okay, sorry, it's y, delta y, so that y coordinate is square root of x minus 0, or just the square root of x. Okay, the distance along the x-axis is the difference, or the delta x, so that's x, okay, minus 3/4. And we're going to call this distance d. Okay, so we've got our triangle, we've got our established distances, and we're just going to apply the Pythagorean theorem, and it looks like we can write it in terms of x. So I'm going to write that as a function in terms of x. Okay, now it's going to be the Pythagorean theorem, okay? So I've got, and then x, square root of x, quantity squared. This is a function. I'm just going to rewrite it here. I'll take the square root of this. Okay, so the square root of x quantity squared is just x. I'm going to close my brackets, write that to the half, and that gets rid of this square feature. So I'm taking the square root to get the straight distance function. I'm taking the square root of this long expression on the right-hand side, and I did a little cleanup here, and I'm good to go. All right, so I've got my function for distance in terms of x. Okay, can I take the derivative of this? That's the next step, always, and we'll see this on the next slide here, this algorithm for doing these types of things. Okay, so let's take the derivative of it. 1/2 first for next here. Okay, and now I have to take the derivative of that inside function. Okay, so a couple of chain rules here. So that's going to be 2 times okay, and then that 1, this 1 is the derivative of this inner function. Okay, and then I've got the derivative of x, which is plus 1. So this actually just kind of cleans up like this. I've got, in my denominator, I've got a 2, that's 2, and then I've got, I'll write it as a square root. Okay, so that gets rid of the negative and the half. And then in the top, I've got this expression right here. Okay, I'm going to clean it up a little bit. I'm going to get rid of the exponent to the power of 1 and then the factor of 1 here. So that's going to be 2x minus 3 halves plus 1. I'm just going to quickly just glance at my notes here, and I'm good. Okay, and that's the one I'm going to take equal to 0. Okay, so let's just clean up the top. That'd be 2. I'm going to distribute 2 into here. That's 2x minus 3 plus 1, and it's all over 2, and then the long radical expression I've got here. Okay. Okay. Now, as we're getting accustomed to, it's this process that I've got to find to do. Okay. And that means I've got to take the numerator of my function. Okay, the numerator of my expression, my derivative expression, is the one that's equal to 0. Could have cleaned this up. X equals 1. Remember that principle that if I have a fraction that equals 0, then only the numerator equals 0. That's the only case. So it's at x equals 1. So it's at the point x equals 1. So at the point x equals 1, okay, right here is pretty much this minimum distance. That's the shortest distance possible. Okay, that's okay as an ordered pair. Okay. That's the point. Okay, P11, okay, is the smallest distance, and that's what we found. Now, if you'd like to go further and actually find the distance at 1, just substitute in the value of x equals 1, add in my function of d, okay, and I think that's probably, this one would be the one we'd use up here, okay, or this one, probably better, it's already as a function of d, so it would be 1, okay, so it would be 1 minus 3 halves, I think it's squared, yeah, and then plus 1, okay, and then I'm going to take the square root of that, so what do we have here? Okay, 1 minus 3 halves is negative a half, quantity squared, plus 1, negative 1 half squared is 1/4, plus 1, that's 5/4, okay, and then the square root of 5/4, what do we write that as? Okay, so this minimum distance is square root of 5/2. Okay, that's it for that one. Just a real simple little analytical geometry, and hopefully you followed that okay and got that. The diagram's a little bit tricky understanding it, but the math is pretty easy, I think, at this stage for us. I want to go one more slide here, okay, and simply just show you the algorithm for optimization, kind of the things we've been talking about, and noticing that these solutions, I hope after doing some of them, following the videos and then doing a couple of homework questions here, you're picking up this algorithm, or this step-by-step. An algorithm is a computer term. It's just a step-by-step instructions for solving a problem, and these are word problems that should be following these basic steps here. Okay, so first up, read and understand the problem. Okay, draw a diagram if necessary. Assign the variables to the quantities involved and state the restrictions according to the situation. Okay, so that's the domain restrictions and any sort of constraints. Identify the variable that is to be maximized and minimized. That's the dependent variable. Write relationships, i.e. equations, for these variables, between these variables. That's the constraint equation. Okay, so what constraint is it under? If you incorporate the interval of the domain. And then the optimal equation. Use the constraint equation to express the dependent variable as one single variable, right? Rearrange the constraint equation and then substitute this new constraint equation into the optimal equation. Find the derivative of the optimal equation, set it equal to 0 to determine the minimum and maximums, okay, and solve for the independent variable. Check the other endpoints, these endpoints, and verify the value from differentiating the optimal equation that this is the optimal point, then write a concluding statement. Okay, that's enough, and we're going to, in our next slide and final slide, we'll talk a little bit about the homework questions, and we're going to do this fun little problem that has a bit of a history to it. A couple years ago, this particular problem made the news, and we're going to work through this and see if we can handle it. So we'll be back at it in our next slide. Thanks.